All right, let's look at this sample problem that's in your textbook that talks about ordering. You're going to be required to do quite a lot of this actually, both in your quizzes and homework and on your tests. So let's look at this. It says, referring only to a periodic table, put these in order from smallest to largest for increasing atomic radius. So if you were to look at a periodic table for the elements phosphorus, sulfur, and oxygen, okay, they're not all in the same period and they're not all in the same group, but phosphorus and sulfur are in the same period, and then sulfur is in the same group as oxygen. So they're basically I'm only looking at this one section of the periodic table because they're all non-metal, so I'm only looking at this one section. So you basically have oxygen up here, and then you have sulfur here and phosphorus here. This is basically what we have. And so what would you know about the three of these, since these are both below oxygen? Then what is going to be true? Okay, both of these are both in the lower energy level than oxygen, so they should both be larger probably than oxygen. And then also, which of the two between phosphorus and sulfur should be larger? Remember the rule, that gets larger as you go down and larger as you go left. Larger down, larger left. So between phosphorus and sulfur, phosphorus should be larger. So between the three of these, what do you think? Between the three of these, oxygen's probably going to be the smallest, and then sulfur, and then phosphorus. And so you just write that oxygen is going to be smaller, smaller than phosphorus, which is going to be smaller. I'm sorry, I wrote that wrong. Larger left. Oxygen is going to be smaller than phosphorus, which is going to be smaller than sulfur. So it's going to be like that. Okay. Well, would you all look at what I just did? If y'all were in my classroom, you would know that I'm a crazy person. I said it right and wrote it wrong. Phosphorus is the largest of all three of these because it's farthest left and farthest down. That's what you have to look at. Which one's farthest left and farthest down low? Farthest left and farthest low, that's how I remember it. Left and low is largest. Left and low is largest. That's how I've always remembered it. Left and low is largest. And phosphorus, of the three of these, phosphorus is the farthest left and the lowest down. So it's going to be the largest. Oxygen is the highest up and the farthest right, so it's going to be the smallest. So that's how you would order those. Okay. All right. And, oh, looky there, we got it right. Okay? All right. And then another one here that's talking about is ionization energy. Now, what I think of when I think of ionization energy, my husband's fond of saying you can't get something for nothing. Even if people say it's free, come and get free, buy one, get one free, he'll say nothing's free, nothing's free. So ionization energy is, now we've talked about this, ions, things becoming ions, and the reason that they become ions is so that they can become like a noble gas. And even elements, when they want to become like a noble gas, they do so because they're trying to get those 8 electrons. They want to be stable like a noble gas. We've talked about electron configurations. The goal is to get there to become like a noble gas. But even though they're trying to become like a noble gas, you can't get it for free. You can't get there for free. And even if they need to lose electrons like magnesium, like the metals, they tend to need to lose electrons so they can become like a noble gas. Even if they need to lose those electrons, you have to give them some energy to strip those electrons away. It costs. So the amount of energy that it costs to give an electron away is called ionization energy. Now, for those elements that are metals, like sodium, like magnesium, like potassium, like calcium, those that want to give their electrons away, that need to become like a noble gas by losing their electrons anyway, they don't require very much energy. But those that have a very high electronegativity, that are very close to becoming a noble gas and need to gain more, they're going to be very stingy about giving their electrons away. And you're going to have to give them a lot of ionization energy to strip their electrons from them. Now, it can be done. It happens all the time on the sun. But there's extremely high temperature on the sun, if you'll recall. So that's the difference. Ionization energy is the minimum amount of energy that is needed to strip an electron away from an element when it's in the gaseous state. That's when it occurs, is when they're in a gaseous state. These are the reactions that happen on the sun. This is the reaction that happened when you were doing your flame tests with your lab. These are the things that are occurring, okay? So, and if they need to lose more than one, let's say magnesium, which needs to lose two, or in this case sodium. When sodium loses this one electron, and this is how you would write it. Here's elemental sodium right here, and it is in the gaseous state. Now then, here it's lost an electron because now it's sodium ion, positively charged, a cation, and there's the electron that it's lost. That's how you could write it. All right. What happens after it's lost that one electron? Now it has this same electron configuration as sodium. It is now isoelectronic. That means it now is acting like sodium. Now, how likely is it that this sodium ion right here is going to give up an electron? How much ionization energy would it cost to get this ion to get it to give up an electron? You would have to give it a lot of energy to get it to release an electron, because now it has become stable and has the same exact electron configuration as sodium. It has reached its goal. And so here, you didn't have to pay it very much. Not very much for that first electron. It doesn't have a very high first ionization energy because it wanted to lose that electron. It needed to lose that electron so that it could reach its goal of becoming like neon. But once it reaches that goal, now you're going to have to pay it a lot to get it to give up that electron. So that's that. Okay? Here are some of the ionization energies. These are in kilojoules. Energy is measured in joules. So this is how many kilojoules per mole, for every mole that you would have to give up. Now, as you would expect, now for hydrogen it's quite high. Look at how high it is for many of the noble gases. Very, very high for many of the noble gases, which you would expect because they are very unreactive. Look at how low they are, though, for those 1A metals, lithium, sodium, potassium. Very low first ionization energy because they need to lose that electron anyway so that they can become like a noble gas. And then look at the halogens over here, look at how high their ionization energies are. Their ionization energies are very high because they don't want to give up their electrons. They need more so they can become like a noble gas. So you'd have to pay them quite a lot. Okay, so you can see the trend as you move across the table. They get higher, their ionization energies get higher. As you move down the chart, they tend to get lower. If you will notice, this is exactly opposite of the size of an atom. The larger they get, the lower the ionization energy is. And if you think about it, it makes sense. The larger the atom is, the farther away its electrons are from the nucleus. And what's holding the electrons to the The protons. And if the electrons are far, far away, way out here, stuck way out here, how hard are these protons going to be able to pull? They're not going to be able to pull near as hard as they can if the electrons are close in. So these protons that are here in the nucleus are going to be able to pull these guys and have a lot more effect on electrons that are close in than they are if they're far out. So large atoms, the larger the atom, the lower the ionization energy. Okay? That, if you think about it, that makes sense. All right. And then it shows you here for your atomic numbers. Okay. And then it asks you this question, sample 7.4, which is on page 289. Would you expect sodium or magnesium to have a greater first ionization energy? And again, since sodium is farther to the left, which would you expect to have the greater first ionization energy? And since sodium is smaller, I just need to stop. It's Monday, and it's been Monday all day for me. I have to draw this. Here's my periodic table. Here's sodium right here. Here's magnesium right beside it. Which one of these two is smaller? Magnesium is smaller. And since magnesium is smaller, it's going to have a higher ionization energy. The larger it is. Okay. All right. And therefore, because ionization energy increases across this way, the size gets smaller, but the ionization energy and the electronegativity both increase going across. Therefore, magnesium is going to have a larger ionization energy. All right. Okay, and then the second ionization energy is going to be much more for sodium, though, because sodium will have already gotten its become like a noble gas, and so you're not going to be able to strip that electron away easily. All right. Okay. And then electron affinity. Please think of electron affinity is how much those atoms want to keep their electrons. That's what that is. Okay. Do they really want to hold on to their electrons? And again, you can associate electron affinity with ionization energy. If they want to hold their electrons and want to keep them, then you're going to have to give them a lot of energy to make them give up. So notice, please, that this is very similar to ionization energy. These guys over here, in the group 1A, again, notice that I'm leaving out hydrogen, have very low electron affinities. They don't want their electrons. They want to get rid of them. They need to get rid of them so they can become like a noble gas. And these guys over here have very high electron affinities. Okay? They really want to keep their electrons and hold them to them. So that's what you can think of electron affinity as being. Okay? It is, you know, how much energy gets released when it gives it up or accepts an electron. That's what you can think of it as being. But to me, it's easiest to think of electron affinity as being hand in hand. There are three terms that you can think of go hand in hand together. Those three terms are ionization energy, i.e. ionization energy, electron affinity, this is the second one, and electronegativity. And of the three of these, electronegativity is by far and away the most important. Oh gosh. These are all identical to each other in terms of they do not have the same definition, but in terms of how they act on a periodic table. And this is the best help that I can give to you. Okay? Get this, please. Get this. Size or radius. Of an atom increases as you go down and increases as you go left. Lower down and to the left increases. Okay? Left and lower is larger for size or radius. I don't care if you call it size or radius. If you want to be scientific, they're going to call it radius. For these three, electron affinity, ionization energy, and electronegativity, the opposite is true. Okay? For ionization energy, electronegativity, and electron affinity, it is exactly opposite. Left and lower is smaller. Right and higher is larger. Okay? So these three are opposite of this radius. And whenever I have to work these problems, I will always put my size in order. And then if it asks me for electronegativity, I just reverse them. I put them in terms of size and then say, oh, it's asking me for electronegativity, so I make them backwards. It may not be very scientific or professional, but that's exactly what I do. Now let's talk about what electronegativity is. Electronegativity is how hard an atom pulls electrons to itself when it's sharing with another atom. Now, we talked about electronegativity when we were talking about covalent bonding. So, again, let's think about it. And again, I may be an unconventional chemistry teacher, but especially at the college level. But I used to have to share a bedroom with my younger sister. We're not very far apart. We're only a year apart. So we always got stuck. We have 4 children in our family. So my younger sister and I always had to share growing up. And you know how that is, or you may not, I don't know. But we would always, if we went somewhere and somebody, we were able to get a toy or get anything, we never got to get 4 of them. My older brother, so he was the only boy, he always got something of his very own. But it always seemed like My younger sister and I had to share. But since she was the younger, for whatever reason, she always got to keep it on her side of the room. Okay? That's the way she was a bully. She still is. That's the way I think of when I think of electronegativity. A good example of this is, let's just say, carbon and oxygen. They are sharing their electrons. They both want to gain electrons to become like a noble gas. And so they agree, okay, neither one of us wants to give up the electrons, so we're going to share them. But they don't share them evenly. Oxygen says, yeah, I'll share them, but I'm closer to becoming like a noble gas than you are. Look, I only need to gain 2. You need to gain 4. So, yeah, I'll share with you, but we're keeping him on my side of the room. So, yes, they share electrons, but they don't share even. They're sharing them closer to oxygen. So we say that oxygen is more electronegative. That's the layman's or the everyday English way of saying what electronegativity is. It's the tendency of an atom to pull electrons to itself in a bond. And electronegativity is actually very important when it comes to molecular shapes. And that we're going to talk about that in a future chapter. All right. This is sample 7.5 problem that's in your textbook on page 291. Okay? It asks you, for each pair of electrons, which one would you expect to have the greater electron affinity? Let's think about what electron affinity is. Electron affinity is how much do those atoms really want to keep their electrons. So between aluminum and silicon, which one of those two would you expect to have a greater electron affinity? Now, for me, I would again say, okay, let's look at these two, aluminum and silicon, atomic numbers 13 and 14. So I would quickly sketch these two atoms. I would draw me a super quick sketch. I'm just drawing me a little periodic table right here. Aluminum is number 13, so here's aluminum right here, and here's silicon right here. Okay, which one is closer to being like a noble gas? Which one is further to the right? Silicon. So which one is going to have a greater first electron affinity? And so that's going to be silicon because it's closer to becoming like a noble gas. It's further to the right. It's going to be smaller, and since it's going to be smaller, it's going to have a higher electronegativity, a higher electron affinity, and a higher ionization energy, all three. It's going to be smaller and have a higher, all three of those. What about silicon and phosphorus? Okay, well, there's silicon already drawn for you, and phosphorus is right next to it. Okay, so between those two, what would you expect? Okay, even though here this is going to be an exception to that rule because of the way phosphorus, the fact that phosphorus is much more stable. So I would not actually ask you this one because you're going to have to do a little bit more math. You're going to use the graph that's on page 290, and in the periodic table that's with it, you can see the electron affinities for phosphorus. And the reason is that according to Hund's rule, notice how many? 1, 2, 3. You know, if we draw our boxes, 2, 1, each one of these. Oh, I don't know why I did that. What I need to do is quit for the day because it's Monday for me. Been Monday all day, and I've made several mistakes today. This one These are your S boxes, and here are your P's. Each one of these has one. That makes it extremely stable. These are my P boxes, and that makes phosphorus be extremely stable. Okay, so silicon, because it does not have this, silicon is going to still have a higher first ionization energy. Okay, so you can look at those kinds of things. All right. So I hope that you think that this chapter is significantly easier. We just have really one more video that we're going to do on this, but I really am going to wait until my mind is working better than it seems to be working today. And that is when you want to compare the size of the actual atom with the size of its ion. And I want you to be thinking about that. Think about that. What if the atom, think of the neutral atom, what if it needs to lose electrons to become like a noble gas? If it loses electrons, is that going to make the ion smaller or larger than its neutral atom? Take magnesium. It needs to lose 2 electrons to become like a noble gas. So is the element, the atom magnesium, going to be smaller or larger than the ion magnesium that has lost 2 electrons? It has 2 less electrons. So is that, which one's going to be bigger? Magnesium or its ion? And the same thing is true. What about one like bromine? Bromine, the element, number 35, or what about bromide that has had to gain an electron, so now it becomes like a noble gas? Which one of those two would be larger, the element or the ion? The difference between the element and its ion, between metals and non-metals. And these are listed for you if you want to go look on ahead. On page 297 you can see them. All right, and then it talks about, the last little bit that we'll talk about are just regular general trends in what to expect of metals and metallic properties and non-metals. And so these are just very much generalities. And so you can see no math, no calculations. So you're welcome.